Today we're going to start section 2.2. It's called Describing Sets. There's a little bit of vocabulary and some symbols and stuff that are going to show up in here so that we're all on the same page. So to start with, if I'm talking about describing sets, you need to know what is a set. A set is any collection of objects. Okay, let's try again. Any collection of objects. So those objects could be numbers. Those objects could be like literal physical objects. Like if I was talking about this classroom of students, you guys would all be in the classroom and all combined together. We would be a set. You are the set of math students who are taking elementary math 1, which is what we call number theory now. If we talk about the listing in my Canvas gradebook, I actually get my own little listing in there, and so does any grader or whatever that I have that have given access to the class there. That would be a set of people, okay? So a set of anything that you would like. The individual objects that are in a set are called elements. So if we're talking about our class, everybody who's meeting in this room right now, we'll go with that one, then each of you would be an element of that set. I would too, because we're all the people who are meeting in this room. When we talk about ways of describing those sets, there's a couple of different ways. A listing method works really well for at least small enough sets to describe like that. So a listing method for a set of numbers. Let me do an example of a set of numbers for each of these so you can see what they would look like. So if we were doing a set of numbers that was 7, 8, 9, and it continues on ... So my ... is understood what I mean next, so I'm allowed to put that. This would be a listing roster method. I would actually list it all out, with the exception of the ... because we know what that's referring to. Not everything can be described very nicely like that. For example, if I wanted to talk about all the rational numbers, which means all the fractions, there's no way to list that out. Okay, there's infinitely many fractions in between any two fractions. I have infinitely many more. There's no way to do that. So there are some times when listing roster methods are just not possible, okay? If we were talking about like all the students at OBU, in theory, right, like we could create a listing method, but that wouldn't be very useful. It wouldn't be very practical, I should say it that way, because I don't want to have a list of 1,800 plus students. That's ridiculous, right? So could I do it? Sure. Is it particularly practical? No. So there might be a better way to do that. So set builder notation is one of the better ways to do that when you have numbers involved anyway, not necessarily for my example about OBU. But let me actually show you what it looks like. So this is an example of each of these. But I'll describe all the details of what I've written down afterwards. So just for now, just write things down with me. So put that funny curly brace. You're going to put the letter X and a vertical bar. You're going to write X is greater than or equal to 7. And then a couple other symbols that you may have not seen before. You're going to do another X. This looks like a script E, and it does need to be curved. Don't go making me a boxy capital E. That's not what this symbol is. This is actually a Greek letter called epsilon. Okay? And then you're going to put the letter N where it's got 2 lines on the left-hand side and close your curly brace. I know, it's like crazy, right? So I want to go to the next slide, which is the next set of notes on your paper where I can identify what some of these pieces are, and then we'll come back and we'll read this after we have that sort of a basis for understanding. So there are a lot of symbols that we use in set notation. The first one I'm going to list is that funny E that I talked about. It is a Greek letter epsilon, okay? It actually means is an element of. So we talked about the word element a minute ago. Element is the objects in my set. So if I talk about the set of people in this classroom, you are one of the elements, okay? What do you suppose would happen if I drew a line through it like that?
It's not an element.
Yeah, it's not an element of.
So is it a lowercase e whenever it is not an element?
It's the same E, it just got a line drawn through it, so it looked kind of funny.
Oh,
Can you see it? It's still that same E, it's just got a line through it. Okay, there are a collection of different symbols where we put the lines, double lines on the left. The N was the one you saw just a moment ago. Okay, so N stands for natural numbers. The natural numbers are also called the counting numbers. So natural or counting numbers. And they're exactly what they sound like. They're the ones that children naturally learn to count with. So if you talk to my 5-year-old daughter, or you talk to your 3-year-old, cousin or nephew or brother or something like that, what number, if you tell them, count to 20 for me, what do they start with? 1. So I'm going to put this in listing method. These are the numbers that start with 1, and they go up to 2 and 3 and 4. None of these children that I just described tell you 3.5. Nobody gives you things like 7/2. Right? These are the counting numbers. So there's your natural numbers. As you work your way through elementary school, these are the numbers you start with. And very soon you run into a problem where you talk about the fact of subtraction and you say something like, I had 3 apples and then Susie ate my 3 apples. How many apples do I have left? And there's not a number that's associated with that in this little set that I've just created. So we introduce the number 0. And once we introduce the number 0, we call that the whole numbers. So they're very similar to the natural numbers. They just include 0. If you see these symbols, like this N or this W in text print, like printed out in your book, what it actually looks like is it doesn't always look like the double lines on the left or the right. Sometimes it will, but it doesn't always. Sometimes what they will do is they'll just bolden the left-hand side where I've put the double lines. But it's really hard to bolden that in your pencil or your pen or on my iPad and make that visibly different. So in written form, we always just do the double lines to indicate that, okay? Okay, so we have these things called whole numbers. Not always the next thing that happens, but one of the next things that happen is we talk about what happens when my son accidentally bought Guardians of the Galaxy 2 on Netflix this weekend. Like it really happened. My husband and I are out on a date. He gets a text from Amazon Prime. It wasn't Netflix, it was Amazon Prime. This has happened on your account. This money has been spent. So my son owes back the $14 for the movie, and in his spend envelope, because we keep it all because otherwise he'd take it to school and he'd spend every dime he ever gets, there's only $6. This is a problem because he owes us 14. 6 minus 14 doesn't work, and we need what kind of numbers to make that make sense? Negative numbers, right? Unfortunately, my son doesn't really understand negative numbers. He just knows that he owes me money still, right? But it's a negative number. That's what it really is. And so when we get these negative numbers, we sort of expand our universe of numbers just a little bit bigger. Oddly enough, it's the letter Z. These are called integers. And they include all the same numbers we've already got, plus the negatives. So in order to write those out in a listing method, we have to put the ... at the beginning, and then we start with -2 or whatever, and then -1, 0, 1, 2, and we continue that ... afterwards. So all the positives and the negatives and 0 that we've already had from before. Somewhere around the same time as integers, kids also are introduced to one other type of number. And it's typically done in either a fraction or a decimal sense first. But whether you view it as a fraction or a decimal, it has the same kind of a name, and it's called rational numbers. Oh, I didn't tell you where the Z came from. Z is actually from the Latin word that stands for integers. I don't know what it is, but that's where it comes from, okay?
Does it have a double line like the?
It does. It has a double line in the middle of it. Yeah, it does.
Weird.
Yeah. Rational numbers is where you get your fractions and your decimals, okay? So rational numbers actually are not an R. They're a Q with that line on the left like this. So these are rational numbers. As I mentioned earlier, rational numbers or fractions are ones that you don't have a way of actually listing them. So the best you can do is something like this. It can be written as a ratio. That's why it's called rational. Ratio means fraction as well, right? Ratio in particular of integers. Okay, so 3 over 2, 2 over 3, -7 over 4. Actually, all those numbers that I have previously also fall into this category, right? How can I write 3 as a ratio of integers? 3 over 1, okay? So this includes everything above. Anybody have any idea why the letter Q might be being used? Okay, Q in this sense is standing for the word quotient. Quotient has to do with division. So when we talk about a ratio of integers, we're talking about dividing integers. So that's where the Q is coming from. And you might be like, okay, fine, but why aren't we using I and R? Because I for integers would be super friendly, and R for rational numbers would be super friendly. And the reason is because they stand for other things. Okay. So I is sometimes used for the imaginary numbers, which is way outside the context of what we're going to talk about, okay? And R is used for real numbers, which is inside of what we're going to talk about, but just barely. So R is for real numbers. And real numbers include all those numbers that are above, but they also include the irrationals. I is also used for irrational sometimes, so that's why I is typically not used at all. So there's 3 things it could be used for, just so you know. So this includes all rational, okay, those ratios from before, and irrational numbers. So let me talk about real quick what irrational numbers are. Kids encounter irrational numbers toward the end of elementary, beginning of middle school in one of 2 fashions. They'll either encounter irrational numbers as radicals like square root of 2. That's a type of an irrational number. Okay, not all square roots, right? Square root of 4 is fine. Okay, but square root of 2 wouldn't work, right? Or they'll encounter it in the form of the Greek letter pi, the number that's representing the ratio of the circumference to the diameter of a circle. So in a geometry kind of sense. Certainly by 7th grade, kids have encountered pi. Okay. So those are irrational numbers. So it's kind of like our world view of numbers just gets a little bit bigger each time. That's the idea. So let's go back to the value that I wrote before that everybody was like, ooh, that's weird looking, and actually talk about what this says now. This part at the beginning just tells you that this is all the numbers that do what happens next. So these are the x values, the numbers. We read this bar as the word such that, or the words such that. All x such that. And then we talk about what those conditions are that has to satisfy. This says x is greater than or equal to 7. I don't think you guys have a problem with that. But I want to clarify that I don't mean all numbers bigger than or equal to 7. Like 7.1 is not in this list, right? So I want to make sure that I don't include it in my description in some fashion. So I have to identify what type of numbers I'm talking about. So this says that they're natural numbers. It also could have said whole numbers, or it could have said integers. Any of those would have worked on this description. But it couldn't have said quotient, right, the Q. It couldn't have said rational numbers, because then it would have included the 7.1, which I was not trying to include. So the 2 pieces of information that are always included when we do set builder notation is a description of the number in terms of the size, right? These are numbers bigger than 7. And a description of what types of numbers. Is it natural numbers, whole numbers, real numbers? You know, what kind of numbers are we talking about? So you always end up with these two pieces of information. They can go in the other order. It doesn't matter. I could say first x is a natural number, right, is an element of the natural numbers. And then I afterwards could say x is greater than or equal to 7. That'll be okay too. Okay. Yes, ma'am.
So, is that like a qualifying statement? So it like cancels out stuff? So like if you don't want it to be an element of natural numbers, you would put a line through the
You could. Yeah,
Okay.
it's not an element of the natural numbers. So you could get all of the numbers that are not whole numbers in a particular set too. Sure.
Okay.
Yep. Okay, so we're going to do just a little bit of practice of going between these types of systems or types of methods, listing method, these types of written methods, we'll say it that way. So it says to write the set of all natural numbers less than 5 using the listing or roster method and then using the set builder notation method. So you need to be careful to tend to the fact that this says natural numbers, right? And that it says less than 5. Those are the two pieces of information. So the listing or the roster method means that we write all the values and do dot, dot, dots if we need them in between the curly braces, and we actually just write them out. So what numbers will be included in my list?
1, 2, 3, 4, 5.
Okay, will 5 be included? No, not this time. It just says less than 5. So 1, 2, 3, 4. Okay. Does 0 get included?
No.
So why was 0 not included?
It's natural.
It's not natural, okay? So, and I don't mean like it's unnatural, but you know what I'm saying, right? It's not that type of a number. All right, so set builder notation, again, has those same curly braces. And it always starts out the same way. We write down x such that. And then the two statements that I've underlined are the statements that I need to write in symbol form. I'll write them in the order that they show up in my description this time. So it says it's a natural number. So we write down x is an element of the natural numbers. And then I also need the statement that says x is less than 5. And that's the inequality x less than 5. And I don't have to clarify that it has a starting spot at 1. The fact that x is a natural number does that for me automatically, so I don't have to worry about that. I just have to make sure that I don't exceed 5, and that's the other part of that. Okay, is that okay for everybody? So we're going to have you go back and forth a little bit between these notations just to get familiar with them. A little bit of vocabulary, a little bit more vocabulary. Equal sets. Equal sets are two sets that contain the exact same elements. So for example, if I talk to you about the set of people in my family, like my immediate family that live in my house, okay, and my husband talked to you about his people that are in his immediate family that live in his house, those would be equal sets. We're talking about all the same exact element group of people kind of thing, right? All the same people. Okay, I'll contrast that to something else in just a minute. A one-to-one correspondence is a pairing of elements between two sets such that each element of one set is paired with exactly one element of another set. So let me just draw out a quick example of that. If I had 1, 2, 3, and A, B, C, and I did this sort of a matching argument, that would be a one-to-one correspondence. A goes to 1, B goes to 2, C goes to 3. If you've ever seen in a newspapers, is it called a cryptogram? I think that's what it's called, where you have to identify the letters and the numbers and you discover a code. My grandmother used to do them in the daily newspaper that she received. And it's a game with one-to-one correspondence involved. Now, equivalent, which grammatically English-speaking kind of things is often used interchangeably with the word equal, is not the same in this context. Equal sets are exactly the same elements in the set, but equivalent sets are simply two sets for which there exists a one-to-one correspondence, i.e. the sets have to have the same number of elements. Okay, so I used to be able to do this wonderful example because there was the same number of people in my family as in my sister-in-law's family, and it doesn't happen anymore because we added 2 kids to our family. So I'm going to create a different example for you. Whoops, I won't do it there. I'll do it over here. Of how that would work with a context. So when my kids go to the lake, which we did over Labor Day, it works best when each child has one playmate. Groups of 3 don't tend to work very well. Sharing is not a good thing with children. I mean, it should be, but it doesn't work very well. So it works much better if there's a one-to-one correspondence of children to somebody else's children. So in particular, the children in my house for whom I'm most concerned is not my 14-year-old who does just fine with adults conversation, right? It's the 10-year-old, the 11-year-old, and the 5-year-old. So I have a sister-in-law, and when they come down, they have a 11-year-old, a 9-year-old, and a 5-year-old, which is pretty close, and it works really well, as long as they're the only groups of kids that come down, right? Because there's a one-to-one correspondence. I have 3 children, she has 3 children of the age I care about in this conversation anyway, and so we can actually talk about those sets being equivalent. Okay, they're not equal, they're not the same children, right? My 3 children are not her 3 children, but they're equivalent because they have the same number of people. Yes. Oh, okay. Sorry, I thought you had a question. Okay. Now, in terms of one-to-one correspondences, obviously in my example, it works best if the 2 boys who happen to be the oldest play together. They're both 11. The 2 girls who happen to be 9 and 10 play together, right? And the 2 littlest ones who happen to both be girls as well, 5-year-olds, play together. But that's just one way that we could structure that correspondence, right? Like in theory, there could be some sort of other arrangements. And that's what this question is getting at, is that if we've got actually 6 elements in each set, how many correspondences could we have? All right? So imagine with me that you were doing one of those, you see them on TV sometimes, right? Like inside of a sitcom or whatever, or inside of a drama, where there's a dating pool thing, right? Where there's like 6 people that show up, 6 guys, and there's 6 girls. And you each move around the room, pairing up to try to see if there's any compatibilities. Y'all know what I'm talking about? You've probably seen them on a show before. Like a speed dating thing, right? Okay, so imagine that. So there's 6 guys and there's 6 girls. And the question is, how many different pairings could there be if everybody paired up with one person when the whole game show was over, kind of deal, whatever, okay? So if you imagine the first line here representing our first, we'll call him a contestant. Okay, and we'll make it be a girl because we can. So we've got one young lady, and she goes into this environment, and she has 6 gentlemen from which to choose, right? So she has 6 choices. But however, after our first lady has chosen, there are not 6 gentlemen left to choose from. Shake your head if you're with me. Okay. So the second lady comes in, and she's going to choose, you know, her match for the evening or her person she's going to sit by or whatever it is, right? How many does she get to choose from? 5. And then lady number 3 comes in. How many choices does she have? 4. The next one has 3. The next one has 2. And the last person is left with what's left over, the last choice. Right, 1. And the way that we would find the total number of ways in which this could happen then is to flat out multiply these numbers together. 6 times 5 times 4 times 3 times 2 times 1. How many combinations, how many different ways could this happen? Anybody know what the number is? 720. It is 720. Very good. There are 720 correspondences. Is it any wonder it's hard for that to actually work? Right? 720 ways it could have worked. That's crazy. That's only 6 people. Well, 12 people, but 6 people on each side of the spectrum, right? Like that's a lot of different ways in which this could have worked out. So there are 720 different correspondences. we'll see this come up, but not in this course, but just in case you've had the other course, I'd like for you to see it before. This 6 times 5 times 4 times 3 times 2 times 1 is actually a specific mathematical operation called a factorial. Maybe you've seen it, maybe you haven't. It's not really part of the curriculum right now, but I just want you to know if you've seen it before, there's a reason why. So that exclamation point is not because I'm excited, it's because it actually has a mathematical meaning called factorial. So just in case you've seen that before. All right, there is actually a name for the number of items in a set. The number of items in a set is called the cardinal number. It's written kind of like function notation is for like algebra. You write an n, you put the set inside capital S in parentheses. It's the number of items in set S. That's how you can think of it. So if we did, right, like for my family, the number of items or the number of people in the set hands household, that number would be 8. Okay, so this isn't all the objects, it's the number of objects, right? But if I wrote down, for example, just hands, this would actually be the people that I'd have to list out. So once I put the n and the parenthesis in front of it, I've turned it into a mathematical operation, an object, a number, okay? A finite set is a set for which the cardinal number is a whole number, right? So like the people at OBU, the people in my family, the books on my bookshelf at home, the contacts in my phone list in my phone, right? Finite number of things. But there are sets of things for which it's not finite, it's infinite. So an infinite set is a set where the cardinal number is not a whole number. Right? It's not a fixed number. The number of natural numbers. I mean, if you really want to, you keep counting for an awfully long time, like forever. Right? You never reach an ending point. There's never a stopping point of the natural numbers. And that's not just them, right? I mean, like that's true for the fractions and it's true for the decimals. I mean, there's not a fixed number of those objects. So those would be infinite sets. And the last one is actually called a null set. A null set is a set that contains no elements. Okay, has a cardinality of 0. There are 2 different ways of writing null sets. One of them is to write brackets with nothing inside of them. So that's sort of like a listing method way. Okay. Another way of writing a null set is to zero with a line through it like this. So this is the point where I need to warn you, if you have the habit of writing your zeros with a line through them already, now is the time to break that habit, because this symbol has another meaning for us. We can't use that to mean the number 0. It's not the number 0. It's the empty set or the null set. Okay, so I'm going to write something that you then immediately have to cross out. So if you choose to write this down, you choose to cross it out. You should never see this written in your notes as an option. What you cannot do is embed the empty set inside of the symbols, you know, with the brackets. That's not okay. Okay? That's not an appropriate notation. So you either use the empty brackets or you use the 0 with a line through it, and that means empty set. Okay. I'd like to jump, this is totally out of order. I really should just change my notes. I'd like to jump to your very last question, and then we'll come back for example 3. Your very last question asks you, create a real life example of the null set in your life.
I have no
Okay?
lines.
So, Valerie, you already spoiled the fun. All right, so I'm going to write mine down. So the null set for me would be babies in my home. Okay, babies in my home.
We have no babies in
I have no babies in my home. I don't. Okay, so I can tell you all about how wonderful the babies are in my home. They're fantastic. They change their own diapers. That's how good they are.
Mm-hmm.
Yeah, they feed themselves. They get themselves dressed in the morning. That's the babies in my home. Okay, I can talk about it like that because they don't exist. Yeah. Okay, so Valerie gave us an example we'll write down for fun. So I'm going to structure it a little bit differently than what you said. So this would be boyfriends of Valerie.
0.
Okay? What would be a null set in your life? Somebody give me another one just for fun.
Pets in my home.
Pets in your home. Okay. So for you, you can write that down. Remind me your name. What is it? Emma? Is that right? Spark? No. Huntley. So these are pets in Emma H's home. See, we got to clarify Emma's home because I have pets in my home. So this would not be a null set for my life, right? Let's do one more for fun.
It said money in my wallet.
Money in your wallet. Okay, so we've got money in Devin, is that right?
Yes.
Devin's wallet. Fabulous. Again, probably not true for everybody in the room. So we need to make sure we talk about Devin being in the description, right? Yeah. Okay, so let's go back then over here to the cardinality question. It was example number 3 where we left off. This problem asks us to find the cardinal number of each of the following sets. So the cardinal number means how many is it that's in this set that's being described. For the sake of being able to use my symbols, I'm just going to call the first set set A, the second set set B, the third set set C, and the fourth set set D. Because what I want to do afterwards is write down that I'm finding n of A. Just for us to have some practice using the right notation. All right. The first set, 9, 10, 11, ... 99. How many numbers are in that description? 90 something, 80 something, what do we do? How do we figure it out? How'd you do that, Valerie?
Well, you go back 1, like minus 1 from the 9, and then that's, yeah. And then you subtract that number from the 19.
Right. So we've done this before, right? That argument where we look at the number before, we say how many are we leaving out? Well, I'm leaving out 8 and everything before it, so 8 is the number I've got to subtract off. 99 minus 8, there are 91 elements, so this has a cardinality of 91. What would I do for set B?
2002 is 0.
Okay, 2002 minus 0. But then what else? Divide by 2. Okay, so I subtract a 0 because that is the number that comes sort of before, right, in my group, my set. Why did I divide by 2? It's only the evens. Yeah, I'm skipping every other number. You got it. And this gives me the number 1001. C and D look weird. They're not listing methods, right? So they look like that set notation method. They're a little different than the ones I gave you examples of before, but you see that X and that bar business going on, right? If it helps you, you can actually write out some elements of the set to give yourself a better idea of the numbers it's talking about. So this says it's all the numbers x squared, where x is this number. So it's 1 squared, 3 squared, 5 squared, all the way up to 99 squared. Okay. Those are the elements of the set. Does the squaring have any effect on the number of items that are there?
No.
Not in the slightest. So it looks way harder than it really is. All I really need to do is to figure out this list of numbers from 1 to 99, how many of those are there? So I need to do something. What do I need to subtract something, okay? So the number that actually comes before in our list here is actually -1, right? So this would be 99 minus a -1. There's 100. Got to do one more thing, though. You need to divide by 2. Why?
Because it's skipping 1.
Yeah, it's skipping, right? Every other number is what's listed. In this case, it's only the odds. So you're right. I do have 100 on top. I have 2 on bottom. So this is giving me a cardinality of 50. Does your C actually say 135?
Yeah.
Okay. Type it on mine. Crazy stuff here. Okay. Last one for today. This says that I want to have all x such that this equation, x equals x plus 1, holds. And it tells you x is a natural number.
So that means that there's no 0, right?
There's what?
There's no 0.
There's no 0. What do you mean by that?
Like, if it was a whole number, it would
Oh,
start with 0, right?
correct. So this list of numbers would be only the natural numbers that you could test. That's true. Annika, right? I'm working on names, but it's just slow coming for this group for some reason this semester. Annika shook her head at me like this almost as soon as I stopped talking. So what were you thinking, Annika, when you started shaking your head at me?
The only number that can make the equation work is 0, which is not a natural number, so it's a null set.
Okay, so half of what you said is spot on, but there's a tiny bit of an error. So 0 doesn't actually work either.
Oh.
Yeah, but the rest of what you said is perfect. There is no number that works here. There's no number that when I add 1 to it, it doesn't change what it was already at, right? Every time I add 1 to the value, it changes it, no matter what I started with. Like, this is absolutely not possible to do. And so Annika's exactly right. What does that mean? Well, it means that this number, this cardinality, I'm actually talking about a funny way of describing the empty set. And the cardinality of the empty set is 0. This is a set with nothing in it. You don't necessarily need to write this here, but I just want you to realize this would be an example of a null set because there's nothing in it. There are no numbers that satisfy that equation and make it true. Any questions on that? All right.